Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have understood the conversion of Moore machine into its equivalent Mealy machine. And now in this lecture, we are going to understand the conversion of Mealy machine into its equivalent Moore machine. So the topic for this lecture is conversion of Mealy to Moore machine. Let's get started with our very first problem. Convert the following Mealy machine into its equivalent Moore machine. So this is the Mealy machine given to us, and we need to convert this Mealy machine into its equivalent Moore machine. Now how do we convert the Mealy machine transition diagram directly into the Moore machine transition diagram without drawing any transition table? Let's see. Move the output values from the transition arrows to the states. That means we have to move the output values from the transition arrows into the states. Why? Because in case of Mealy machines, the outputs are associated with inputs over the transition arrows. But in case of Moore machines, the outputs are associated with the states. That is why we are required to move the output values from the transition arrows into the states. And if multiple outputs enter the same state, then we have to create the separate states for each distinct output. Now, while shifting these output symbols from arrows into the states, there can be a possibility when multiple outputs enter the same state. So that is not allowed in case of Moore machine. In that case, we need to create the separate states for each distinct output symbol. Suppose if I shift this A into this particular state, that is B. Also, if I shift B into this state, that is B. So this state will be having two output symbols, A as well as B. And that is not allowed in case of Moore machine. In case of Moore machine, one single state will be associated with only one single output symbol. So in this case, we need to create two separate states. First state B will be having output symbol A, and the second B will be having output symbol B. In this way, we will create two separate states for each distinct output symbol. You will understand this step more clearly when we apply this step. So now, this is the Mealy machine that is given to us, and now we will apply the same process to convert this Mealy machine transition diagram into its equivalent Moore machine transition diagram. Let's start with the initial state, that is A. So here we will draw the initial state, that is A. Now, for this transition, you can see the state A, on getting input symbol 0, we are reaching the state B. And for the state A, on getting input symbol 0, we are getting the output symbol A. So overall, we can say for the state A, if the input symbol is 0, we will reach the state B, and that B should have the output symbol A. So we can represent this like A, on getting input symbol 0, we will reach the state B having output symbol A. So this A is shifted from this transition arrow into this particular state to convert this into a Moore machine. I hope this transition is clear to you. I repeat, A, on getting input symbol 0, we will reach the state B, and that B should have output symbol A. A, on getting input symbol 0, we will reach the state B, and that B should have the output symbol A. In this way, we have created the very first transition of the Moore machine. Now, we will draw the transition for the state A on getting input symbol 1. A, on getting input symbol 1, we will reach the state C, and that C should have output symbol A. So A, on getting input symbol 1, we will reach the state C, and this C should have output symbol A. This means this output symbol A is shifted from this transition arrow into this particular state, that is C. So we have created the two transitions for our Moore machine. Now we have to create the transitions for these two states for both the input symbols, 0 and 1. Let's start with this state, that is B. Now here you can see B, on getting input symbol 0, we will reach the same state B, but this B should have the output symbol B. Now can I create a self loop over this state also? If I create a self loop, B, on getting input symbol 0, we will reach the same state B, but this B is having output symbol A. And according to this, B should have output symbol B. So to represent this scenario, we need to create the separate states. Why? Because if I create a self loop, then this B will also enter this state, and this state will have two output symbols, A as well as B, and that is not allowed in case of Moore machine. So we have to create a separate state. So B, on getting input symbol 0, we will reach the state B, but this time, this state B is having the output symbol B. I hope this transition is clear to you. Now we will create the transition for state B on input symbol 1. B, on getting input symbol 1, we will reach the state C, and this C should have output symbol A. That means this output symbol A is to be shifted from this transition arrow into this state. So C with output symbol A we already have. So B, on getting input symbol 1, we will reach the state C having output symbol A, perfectly represented using this particular transition. So we have completed both the transitions for the state B. Now we will complete the transitions for this particular state, that is C. C, on getting input symbol 0, we are reaching the state B, and this B should have output symbol A. So we have B with output symbol A, so we can directly draw the transition. C, on getting input symbol 0, we will reach the state B having output symbol A. Now let's talk about C for the input symbol 1. C, on getting input symbol 1, we will reach the same state, that is C, but this time the output symbol should be B. Similarly, we cannot create the self loop for this state, because if I create a self loop, C, on getting input symbol 0, we will reach the same state C, but output is A. Here we can see the output should be B. If I create a self loop, then B will also enter the same state, and that is not allowed as per the rule. In case of Moore machine, only one output symbol can be associated with one state. That is why, to represent this transition, we need to create a separate state, that is C having output symbol B. So C, on getting input symbol 1, we will reach the state C having output symbol B, denoted by this transition. C, on getting input symbol 1, we will reach the same state C, but this time C should have output symbol B, denoted by this state. In this way, we have completed the transitions for the state C as well. Now we have two newly created states, B having output symbol B and C having output symbol B. So we need to complete all the transitions for these two states also. Let's first complete the transitions for this state, that is B. Now B, on getting input symbol 0, we will reach the same state B, but B should have output symbol B. This B is already having output symbol B. Now we can simply create the self loop for the input symbol 0 over the state B, because now B, on getting 0, we will reach the state B having output symbol B, perfectly denoted by this transition. Now, what will be B on input symbol 1? So B, on input symbol 1, we will reach the state C, but we will reach that C having output symbol A. So C having output symbol A is this particular state. So B, on getting input symbol 1, we will reach the state C having output symbol A. Now we will complete the transition for this state, that is C having output symbol B. Now C, on getting 0, we will reach the state B having output symbol A. That means C, on getting input symbol 0, we will reach the state B having output symbol A. we will not reach the state B having output symbol B. We will reach the state B having output symbol A. Why? Because here you can see C on getting 0, we will reach the state B, which should have the output symbol A. That is why I have made this particular transition. Now, C on getting input symbol 1, we will reach the same state C, but it should have output symbol B. Now we have C having output symbol B. So we can simply create a self loop. C on getting input symbol 1, we will reach the same state C having output symbol B. So this is the Mealy machine that we have created till now. Now there is a small problem in this diagram. As you can see, these two states have the same name, that is B. And these two states also have the same name, that is C. This can be confusing. So we will modify the names of these two states and these two states so as to identify them individually. Like this. As you can see, I have changed this B into BB. Why? Because this B is associated with output symbol B. Similarly, I have changed this B into BA because this is associated with the output symbol A. Similarly, I have changed this C into CA because it is associated with output A, and I have changed this C into CB because it is associated with output B. Now you can uniquely identify each state because all the states are having the different names now. Now is this Moore machine complete? No. Still one more issue is left. As you can see, this is the initial state of the Moore machine, and this is not associated with any output symbol. In case of Moore machine, every state should be associated with an output symbol. All the states are associated with an output symbol, but the state A is not associated with any output symbol. Why? Because our original Mealy machine does not have any incoming edge towards A. So we will create a dummy output symbol for the state A, like hash. But it is to be noted, while generating the output string from the input string using this Moore machine, the first output symbol, that is hash, will be ignored. Why? Because you already know, in case of Moore machine, it will give the first output symbol even without reading any input symbol. That is why we have to reject or ignore the first output symbol. So here, hash is the dummy output symbol that we have created. Now we can say this as a complete Moore machine that we have constructed by converting this Mealy machine into its equivalent Moore machine. In this way, we have solved our problem number 1, in which we have directly converted the Mealy machine transition diagram into the Moore machine transition diagram without drawing any transition table. Now we will proceed towards our second problem. Convert the following Mealy machine into its equivalent Moore machine. Now this is the transition diagram of Mealy machine given to us, and we need to convert it into the transition diagram of Moore machine. But this time we will use a different approach. This time we will not directly convert the transition diagram of Mealy machine into the transition diagram of Moore machine. We will solve this problem using the transition table approach. So we will first convert this Mealy machine transition diagram into the Mealy machine transition table. Then we will convert the Mealy machine transition table into the Moore machine transition table. And finally, we will convert the Moore machine transition table into the Moore machine transition diagram that we want as per our problem. Why I am following this approach? Because sometimes the diagrams are very complicated. So following the previous approach is not very convenient. So in your examination, when you will get a question to convert a Mealy machine into its equivalent Moore machine, you can follow any of the approach that is suitable to you at that time according to the complexity of the problem. So let's solve this problem using the transition table approach. But first you have to tell me, do you find something weird in this particular Mealy machine? Yes, this state Q2 is a disconnected component from these three states. But so what? Then also this Q2 will be the part of this Mealy machine only. The state Q2 is unreachable from the initial state Q0. But even if it is unreachable, then also we can convert this whole Mealy machine into the Moore machine. We don't need to worry about that this Q2 is a disconnected component. Even if it is a disconnected component, it can still be converted into its equivalent Moore machine. So we will consider this whole as one particular Mealy machine and we will convert this into its equivalent Moore machine. So this is the Mealy machine given to us in the problem, and the first step is to convert this Mealy machine transition diagram into the Mealy machine transition table. This is the basic structure of the Mealy machine transition table. As you can see, the present state and the current input symbol determine the next state as well as the output according to the definition of Mealy machine. Now we have to fill all these entries according to this particular transition diagram. Q0 on A gives Q3 with output 0. So Q0 on A is giving the next state Q3 and output symbol 0. So here we will write Q3 and output symbol 0. Now Q0 on B. So Q0 on B is giving us Q1 and 1. So here we will write Q1 and 1. Q1 on A. Now Q1 on A is giving us Q0 and output 1. So we are getting Q0 and output 1. Q1 on B. Now Q1 on B, we are getting the next state Q3 and output 0. So we are getting Q3 and 0. Q2 on A. Now Q2 on A is giving Q2 and 1. So we are getting Q2 and 1. Now Q2 on B. Q2 on B, we are getting Q2 and output 0. So here we will write Q2 and 0. Now Q3 on A. Q3 on A gives us Q1 and 0. So here we will write Q1 and 0. Q3 on B. Now Q3 on B is giving us Q0 and 1. So here we will write Q0 and 1. This is how we have completed our transition table of Mealy machine from the transition diagram of Mealy machine given to us. So this is the transition table of Mealy machine. Now we need to convert this into the transition table of Moore machine. But to convert it into the transition table of Moore machine, we need to follow some steps. For all the states, examine the outputs on all the transitions entering that state. What does that mean? It means that for all these states, we need to examine the output symbols received by these states. And if a state receives more than one distinct output symbol, then we have to split that state into separate states for each output symbol. That means if a state is receiving more than one output symbol, then we have to split that state and we will create the separate states having different output symbols. So let's check all the states. Let's start with the state Q0. Q0 is receiving output 1. Let's check if there is one more Q0 or not. Yes, Q0 is again receiving output 1. That means Q0 receives output 1 and Q0 again receives output 1. So basically, Q0 receives only one output symbol, that is 1. So it will not be splitted into the separate states because it is not receiving more than one output symbol. Now let's check Q1. Here we have Q1. Q1 receives 0. Again, Q1 receives 1. That means this time Q1 receives 0 and this time Q1 is receiving 1. So Q1 receives two output symbols, 0 and 1. That means Q1 is receiving more than one output symbols. That is why we will split Q1 into two states, Q1 0 and Q1 1. Now what is Q1 0 and Q1 1? Q1 0 means Q1 having output symbol 0 and Q1 1 means Q1 having output symbol 1. So this Q1 0 is associated with 0 and this Q1 1 is associated with output symbol 1. Now let's check Q2. Q2 is receiving 1 and Q2 is receiving 0. So Q2 is also receiving two output symbols, 0 and 1. So we will split Q2 into two states, Q2 0 and Q2 1. Q2 0 means the state Q2 associated with output symbol 0, and Q2 1 means the state Q2 associated with the output symbol 1. Now let's check the state Q3. Q3 receives 0 and Q3 again receives 0, which means Q3 receives only one output symbol, that is 0. So we will not split Q3 into the separate states. So finally, this is the transition table of the Mealy machine, and we will split Q1 into two states, Q10 and Q11, and we will split Q2 into two states, Q20 and Q21. So in the Moore machine transition table that we will get, we will not have the state Q1 and Q2. Instead of Q1, we will have Q10 and Q11, and instead of Q2, we will have Q20 and Q21. But Q0 and Q3 will remain as it is in the Moore machine transition table also. So this is the structure of the Moore machine transition table, and as you can see, we have Q0 as it is, but instead of Q1, we are having Q10 and Q11. Instead of Q2, we are having Q20 and Q21 because Q20 and Q21 are splitted from Q2, and Q3 is as it is in the Moore machine table also. And in this Moore machine table, you can see only the present state is determining the output symbol, not the current input symbol, as per the definition of the Moore machine. Now we have to fill all the entries of this table by using this particular transition table of Mealy machine. So we will start by filling the output column first. Now Q0 was associated with the output symbol 1. That is why I will write 1. In the previous slide only, I have explained you that Q0 receives only one output symbol, that was 1. Now what about Q10? I have explained you the meaning of Q10. Q10 means the state Q1 which is associated with output symbol 0. That is why we will write 0. Now Q11 means the state Q1 associated with the output symbol 1. So here we will write 1. Now Q20 means the state Q2 associated with output 0. So here we will write 0. Now Q21 means the state Q2 associated with output symbol 1. So here we will write 1. And in the previous slide you have seen that Q3 was receiving only one output symbol, and that was 0. That is why I have written 0 here. In this way we have completed the output column of this table. Now we have to fill the next state column for the input symbol A as well as for the input symbol B. As you can see, Q0 on A gives Q3, and Q3 is a state in Moore machine. That is why we can write Q3. Now Q0 on B gives Q1, but Q1 is not a state in Moore machine. Q1 is divided into two states, Q10 and Q11. So which of the following we will write here, Q10 or Q11? Let's check. Q0 on B is giving Q1 associated with output 1, and Q11 means that Q1 is associated with output 1. That is why here we will write Q11 and not Q10. Now let's check for Q10 on input symbol A. Q10 is a derivative of Q1, so we will check Q1. Q1 on A gives Q0, and Q0 is a state, so we can write Q0. Now Q10 on B. So Q1 on B gives us Q3. Q3 is a state in Moore machine, so we can write Q3. Now Q11 is also a derivative of Q1. So similarly, we can write Q0 and Q3. Now let's talk about Q20. Q20 on A. Now Q20 is a derivative of Q2. So we will check the transitions of Q2. Q2 on A is giving us Q2, but Q2 is not a state in Moore machine. So here we cannot write Q2. We have to write either Q20 or Q21. Let's check. Q2 on A is giving us Q2 associated with 1. Now Q2 associated with 1 is called as Q21. So here we will write Q21. Now Q20 on B. So Q2 on B is giving us Q2 associated with 0. And Q2 associated with output 0 is called as Q20. So here we will write Q20. Now Q21 is also a derivative of Q2. So we can write Q21 and Q20 as it is, like Q20. Now we will fill the transitions for the state Q3. Q3 on A. Now Q3 on A is giving us Q1. But Q1 is not a state. So Q1 is associated with 0. And Q1 associated with 0 means Q10, this state. So here we will write Q10. Now Q3 on B. Q3 on B is giving us Q0. And Q0 is a state. So we can write Q0. In this way, we have got our Moore machine transition table that we have converted from our Mealy machine transition table based on some predefined process. So this is the Moore machine transition table that we have received. Now we will convert this Moore machine transition table into its corresponding transition diagram. So first we will draw all the states. Q0 associated with output 1 because Q0 is associated with output 1. Q10 associated with 0, that is Q10 associated with 0. Next is Q11 associated with 1. So Q11 associated with 1. Next state is Q20 associated with 0. So Q20 associated with 0. Next we have Q21 associated with 1. So Q21 associated with 1. And last one is Q3 associated with 0. So Q3 associated with 0. So these are all the 6 states that we have drawn according to this transition table. Now we have to create all the transitions. Q0 on A is giving us Q3. So Q0 on A is giving us Q3 and Q0 on B is giving us Q11. So Q0 on B is giving us Q11. Now Q10 on A gives Q0. So Q10 on A is giving us Q0 and Q10 on B is giving us Q3. It is giving Q3. Now let's talk about Q11. Q11 on A gives Q0. Q11 on A gives Q0 and Q11 on B gives Q3. Q11 on B gives Q3. Q20 on A gives Q21. Q20 on A gives Q21 and Q20 on B gives Q20. Q20 on B gives Q20. Q21 on A gives Q21. Q21 on A gives Q21 and Q21 on B gives Q20. Q3 on A gives Q10. Q3 on A gives Q10 and Q3 on B gives Q0. Like this. So this is the transition diagram of the Moore machine that we have constructed using this transition table of Moore machine. Now we can see that this was the original Mealy machine given to us and this is the Moore machine that we have constructed by converting this Mealy machine into its equivalent Moore machine. And you can see the original Mealy machine has 1, 2, 3, 4 states and the resultant Moore machine has 1, 2, 3, 4, 5, 6 states. That means while converting a Mealy machine into Moore machine, the number of states may increase. In the previous lecture, I have explained you, while converting a Moore machine into its equivalent Mealy machine, the number of states remains the same. But here, the number of states may increase. So there is one important point to note. If a Mealy machine has X states and Y distinct output symbols, the equivalent Moore machine can have at most X into Y states. What does that mean? It means if a Mealy machine has X states. Now what are the number of states in the Mealy machine? 1, 2, 3, 4. So X is equal to 4. And Y distinct output symbols. How many distinct output symbols are there? 0 and 1. That means only 2. So X is equal to 4 and Y is equal to 2. Now, the equivalent Moore machine can have at most X into Y states. That is 4 into 2 is equal to 8 states. That means the equivalent Moore machine can have maximum of 8 states. It cannot have more than 8 states. As we have already seen, it has 6 states. That means it is allowed, but it cannot have more than 8 states. 8 is the maximum number. So if the X states and Y distinct outputs are there in the Mealy machine, then Moore machine can have at most X into Y states. That is the meaning of this point. So now I hope you have understood this problem perfectly. Obviously, it is not a very straightforward problem, so you have to practice it to get a good grasp over such problems. In this way, we are done with our topic, conversion of Mealy to Moore machine, and with this, we are done with the chapter number 2, that is finite automata. From the next lecture onwards, we will start our new chapter, that is chapter number 3, regular expressions. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.